In the last video, we introduced what we meant by a group and we started to look at a few groups, but we focused on ones where we were either doing multiplication or addition or a similar arithmetic operation. I want to extend what we know about groups now to a few different cases. One that comes very much from geometry, and one that comes from something entirely different altogether. So the first one we're going to look at is going to come by thinking about the geometry of an equilateral triangle. So I'm going to take an equilateral triangle here, and I'm going to label the vertices A, B, and C. Now, if this is an equilateral triangle, there's a few possible symmetries going on. I'd recommend you pause the video for 5 seconds and try and name all the symmetries. But we've got two main types of symmetries here. We've got reflective symmetries and we've got rotational symmetries. So our rotational symmetries, it's order 3, so we could either rotate by 120 degrees clockwise or rotate by 120 degrees anti-clockwise. I'm going to introduce names for all these here. So I'm going to say that if I'm rotating by 120 degrees anti-clockwise, I'm going to call this operation R1. So that's taking ABC, if we're going 120 degrees anti-clockwise, to A is going to be the bottom left, B here, and C up here. And similarly, R2, I'm going to say, is the one that's 120 degrees clockwise. So that's going to be taking ABC to our triangle where A is the bottom right, C is the bottom left, and B is the top. So there are two of them. But we've also got our reflective symmetries to worry about. So we've got 3 lines of reflective symmetry. We've got this vertical one, which I'm going to consider as my first reflective symmetry. So I'm going to say that if I do ABC and do reflection 1, now I've already used that, so I'm going to choose a different letter. I'm going to say if I do the symmetrical reflection 1, that's a reflection in my first line. So it becomes A and then CB, like this. So A stays as it is, the others change. And then we've got 2 more to consider, which are going to be the second one. As you can see, this is going to be a fairly arbitrary label, and I'm going to consider this to be S2. So we're going to have ABC reflected in that line. B is going to stay where it is, and RA and C are going to switch. And unsurprisingly, my S3 is going to be my final line here. So S3, C is going to stay where it is, and A and B are going to switch. Now, there's actually one more option that I really should be considering here, because unsurprisingly, given the title of the video, I want to consider the group made up of these different operations, these different reflections and rotations. Now, one axiom from the group we absolutely always need is we need to have an identity element. All these are changed in our triangle. So the final one I'm going to consider is the do nothing option. So the do nothing option, obviously ABC stays exactly as it is. It kind of does what it says until it does nothing. By convention, I'm going to call our identity operation E. You don't have to, but that's the most commonly chosen letter for our identity. So we want to consider that this is a group. So a few things to go through straight away. Well, we know we've got an identity now, and that's in our group. So our group's going to consist of our elements E, R1, R2, S1, S2, S3. We need every element to have an inverse in the group. Now, the inverse of R1, if we rotate it 120 degrees anti-clockwise, would be R2, which is rotating it back, and similarly, the inverse of R2 will be R1. All reflexive symmetries, if we do S1, then doing S1 again will reflect it straight back. So it's going to have an inverse, same for S2 and S3. So it's got an identity, it's got an inverse. We'll investigate closure in just a second. And because rotations really are just functions, and also we can represent any rotation as matrix multiplication if we want, we know this is going to be associative. So we fit, as long as we've got closure, it's going to fit everything we're expecting of a group and our group axioms. But how are we going to go about forming our Cayley table now and showing what's going on? Well, let's consider a couple of specific ones. I'm not going to go through everyone here. That will be a little task for you. But let's have a look at some first. So the first thing I want to consider, what's going to happen if we do S1 followed by R1. So in this case, we're starting, as always, with triangle ABC here, just to make it easy to think about. We might as well always choose the same one. If we do S1 first, what's going to happen? So our A stays exactly where it is, and our B and C switch here. And then we want to do R1. Now, R1 was a rotation 120 degrees anti-clockwise. So this is then going to have A comes down to the bottom left, C moves across to the bottom right, and B goes up here. What we want to do is describe this as a single transformation. Well, if we look what's happened from our first triangle to our last triangle, C stayed exactly where it is, and simply B and A have switched. So this is simply reflection through that line through C, and that's exactly the operation we've called S3. So, as with need for closure, these doing S1 and R1 is exactly the same as doing S3. The composing these two geometrical transformations is the same as another one of our geometrical transformations. Now, in the same way when we compose functions, we should be careful here. What we've done S1 first, and then we've done R1, but we're going to write this as R1 composed with S1 because in the same way with functions, it's the rightmost one that happens first. And we know that this is equal to S3. Now, if we were to go in the other order here, if we were to do R1 and then S1, and if you're feeling confident, I'd recommend you pause the video now and just give it a go first. So that one absolutely doesn't look like a 1, so I'm going to rewrite that. R1 and then S1, let's just consider what we've got here. So we're going to be taking our triangle ABC. We're rotating 120 degrees anti-clockwise. So it becomes A down to the bottom left, B bottom right, and C here. And then we're reflecting through this vertical line here. So the C is going to stay where it is, and the B and A and are going to switch. And now if we look what's happened from our start to our end, well, the B stayed exactly where it is overall from our first triangle to our last triangle, and the C and A have switched. So this is the equivalent of S2. So if we do R1 first, and then we do S1, and again, similar to function composition, I'm going to write the R1 rightmost if that's the one happening first. This is the same as S2. Now, what this is going to allow us to do is to start to make a Cayley table. So what I want to get here is I want us to be able to make a Cayley table where we're doing function composition. I'm just going to do a little circle to represent function composition. And along the top, I want to consider if we've got E, R1, R2, S1, S2, S3, all the elements of our group. As long as it's closed, it'll be a group. And E, R1, R2, S1, S2, S3. Now, where should we be entering our entries onto this? We know that R1 composed with S1 is S3. So it's R1 from here and S1 up here. Those composed in that order gives us S3. So below those, I'm going to put an S3. Whereas if we go S1 first and then R1, we're going to get S2. So that S1 first and then R1 is going to be what goes here. I'm going to challenge you to fill in some of these others. I'm going to touch on a couple of them, and then I'm going to leave the rest to you to have a think about. So because easy identity, this should be a nice, easy row to fill in. It's not going to change. If we do either R1, the overall effect's just going to be R1. So that's a nice, easy row to fill in. And similarly, the column with these is a nice, easy column to fill in as long as I don't do it wrong. So R1, R2, S1, S2, S3. So far, so good. Now, getting these others a bit more of a challenge. My recommendation is you pause the video for a few minutes, try going through this, filling them in. Now, I prepared earlier, so I'm just going to go across here and steal it for you. So this little table here, if we pop back over, I'm just going to pop in, and we should be able to compare and make sure that you agree with our options here. Now, just a couple of ones to pick up on here. Do our inverses match up with what we're expecting? We're expecting all our reflective symmetries to be self-inverses, and that's what we've got here, because if we do S1 composed with S1, we get E. S2 composed with S2, we get E, and so on. So that matches up. And the other thing we should notice is we've got complete closure of our group. Any combination of any of our group composed with any of our group gives us something else in our group. We can also check, we've got this Latin square property, each entry appears in each column exactly once, and in each row exactly once. So that's a nice check there. So that's one sort of group that we can look at, which is a geometric group. Now, this group gets a special name of the dihedral group of order 6. The reason it's order 6 is because we have 6 elements in this. I'm going to now look at a group that looks completely unrelated, and then at the end, hopefully we'll spot that there is actually a connection going on here. So the next thing we're going to look at doesn't have any geometrical relation interpretation immediately. Instead, we're going to think about permutations. Now, you might have heard of permutations doing statistics. We're really thinking about number of ways of arranging something. It comes up in binomial expansion to an extent as well. So I'm simply only going to think about 3 elements because there's only so many ways of arranging 3 distinct elements. So if we start with the elements 1, 2, and 3, and I want to arrange them in some order, well, firstly, how many ways do we have of doing this? We've got 3 choices for our first element. Then once I've chosen my first element, I've got 2 choices for my next element and 1 choice for my next. So I should have 6 ways of arranging these. I want each of these ways, each of these reorderings of 1, 2, 3, to be considered as a permutation, and we're going to consider these as our functions now. So I'm going to start off, the most boring permutation we can have is the do-nothing permutation. So we start off with 1, 2, 3. I'm going to explain my notation in a second. Then we go to 1, 2, 3. What my notation here means, and I wouldn't normally write these arrows in, is 1 is being mapped to 1, 2 is being mapped to 2, and 3 is being mapped to 3. So if we start with 1, 2, 3, we finish with 1, 2, 3. That's one way of ordering. Calling it a reordering is probably an exaggeration. But we have other options here. So another option here might be, which I'm going to call my permutation P, might be I start with 1, 2, 3, and I reorder them, I move them all along one. So 1 becomes 2, 2 becomes 3, 3 becomes 1. That's another reordering I could do there. And a third one I could do, in a similar vein, rather than shifting them all one to the right, is shift them one to the left. So 1, 2, 3 could become 3, 1, 2 here. Now, these aren't the only possibles, because let's have a look. We could have one where maybe we don't move the element 1 at all. 1 stays in the first place, but 2 takes 3's place, and 3 takes 2's place. And then similarly, I'm going to say that V2 stays where it is, but 1 and 3 switch. And for the final one, W, I want to say, unsurprisingly, that 3 stays where it is, and 2 and 1 switch here. So what I want to consider now is what happens when we compose these permutations. So we'll go through a couple of cases, and again, we'll try forming a Cayley table and show that these 6 permutations are going to form a group, and hopefully we'll spot a connection between this group and this geometrical group. It's worth considering for a few seconds before we get into it, if you can predict what that connection might be, but we'll get into doing those now. So let's consider how we might compose these permutations. So what if I wanted to compose the permutations UP? Well, let's consider an element at a time. If we do, where's element 1 going to end up? Well, if we do UP of 1, we can see that under permutation P, 1 gets mapped to 2. So this is doing U of 2, and then under permutation U, 2 gets mapped to 3. So UP of 1 gives us 3. So we've got 1 is being mapped to 3. If we do UP of 2, then under P, 2 gets mapped to 3. So we're doing U of 3. And under U, 3 gets mapped to 2. So we get 2 ends up being mapped exactly to 2. And then we've got UP of 3. Well, under permutation P, 3 gets mapped to 1. So we're doing U of 1. And under U, 1 gets mapped to 1. So that stays as 1. So 3 ends up going to 1 here. So we can say that UP is the permutation. We'll start on 1, 2, 3. 1 gets mapped to 3. 2 gets mapped to 2. 3 gets mapped to 1. well, what is this? Let's compare. This is exactly permutation V. So UP is equal to V there. Notice again, when we're writing UP, we're doing permutation P first, and then we're doing permutation U. So if we want to draw a Cayley table for this one, then we're going to get something similar to what went on in the last one here. So I'm going to do a little Cayley table here. I'm just following off the screen. So what we're going to have is I'm going to say we've got E and then P, Q, U, V, W, E, P, Q, U, V, W. Where am I going to put this UP equals V? We're doing U here composed with V here is going to be equal to V. So, sorry, that's not the one I want. U composed with P is equal to V, so that's where we're going to put V. Other easy things to fill in, as always, we can quickly fill in our tables here. That should be no problem whatsoever. And then we want to start to fill in other little elements. I'm going to encourage you to pause the video, try and fill the rest of those in. And once you rejoin me, I've got one that I prepared earlier. So I'm going to go over to this bit now, and there's a reason for that. So the second one you should end up looking exactly like this table on the right here. Now, the last thing I want to notice is these aren't too dissimilar. Okay, there's a lot of letters going on, so it might be hard to see any patterns straight away. But one thing, well, firstly, both the groups have 6 elements. A fancy way of saying that is that the groups have order 6. That just refers to the number of elements when we're talking about finite groups, at least here. So if we're then comparing what's going on, well, our identity is E in both of them. And that's nice and easy to compare. I'm just going to highlight those so those match up nicely and they're at exactly like identities. That's no big surprise here. Now, the next thing I want to notice is if we just relabel, if we took all our elements in our second group and relabel them, because remember, it wasn't necessarily I chose P, Q, U, V, and W. If I'd chosen to label them R1, R2, S1, S2, S3, then all our entries would change in exactly the same way. If I just chose to relabel like this, the relabeling would give us exactly that first group there. This is called an isomorphism, where those two groups really essentially have exactly the same structure, but it just comes down to the way we label them. Then that's what we call a group isomorphism. Now, in terms of finding group isomorphisms, there's going to be another video following looking at that and looking at the fast ways of doing it, because it's not always going to be this easy to spot. And in this case, it was particularly nice because I put the ordering in the exact same ordering of both groups. But finding these is really useful, because that means that if we're able to think about something maybe geometrically to get results about permutations or vice versa, we can do, because really there's the same thing in disguise. If we can prove group results about one group, the results about the other group are going to come out straight away, and that's going to be really useful for us. But there'll be more about isomorphisms in the next video. Thank you very much.